I mean, you have red no matter what, but you're sitting through.
I forgot to update my driver license.
Alright, let's have a quick review of last class. We had this energy equation. After all this derivation, we ended up in this formula for steady state, incompressible, but in this case you may have friction, you may have loss. So this equation is superior to Bernoulli equation because it includes the loss, friction. You see, in fact, the friction, when we talk about friction, we're not talking about always loss. We also talk about the work coming from pump and turbine. Those all come from the surface friction of these devices. If you don't have friction, these devices, in fact, they don't work. You're not going to get any work out of the pump, or you don't generate any work from the fluid because there is a friction. No rotation on the turbine blade. You see that? So this equation is an energy equation, but you can immediately see that. We said that if you have frictionless and all those assumptions we had before, you get rid of this H, the head from the loss, the turbine, the pump, and then you get our Bernoulli equation back. But look, this is even more comprehensive than the Bernoulli we derive from the momentum, because when we derive the Bernoulli from the momentum equation, we made the assumption that we integrate over the streamlines. We gotta find the streamline between 2 points, right? And if we change the streamline, that means if we change 2 points, the constant of integration will change, C1, C2. So we had a lot of limitation. But look, if you make this assumption, there is no heat loss, there is no friction, there is no nothing like that. This Bernoulli not only is between these 2 points, but also between any point in the field. And you can immediately justify that by just considering this basic fact. You go from this point, let's say this will flow, 1, 2, right, 3, 4. Now, assuming that we have rotational flow, so every particle here is kind of rotating. You see that? So you have kind of twist. You see that? Now you can say that when I go from this streamline, across this streamline I have this 1/2 of rho v squared plus rho gv plus P plus rho gz is equal to constant, say C1. But you can say that because of this, now from the energy concept, because this sum is just the head, is the energy head. Because if you go from this streamline to the next one, there is a lot of particle rotating. So you kind of adding or subtracting that rotational energy. You had it in dynamics, if you had an object like that, and this object was rotating the angular velocity omega, right? What was the energy? The energy of that was what? The kinetic energy was 1/2 of I omega squared. You had this in dynamics. Now imagine, look it from the top, each one of these particles on the cylinder like that. So the moment you go from this streamline to the next one, if the flow is rotational, this constant will change, C1 and C2. But if the flow is irrotational, what happens? That means you don't have it. You don't have all this. That means when you go from here to here, this constant is same, right? C1, for this, you have 1/2 rho v squared plus P plus rho g is C2. So in that case, if there is no rotation, these heads are same. That means you have this relation, 1/2 rho v squared plus rho gz plus P is equal to between this streamline is equal to the same sum between the other streamline. And because these are arbitrary, that means this sum is valid between any streamline in the flow. In other words, this sum is valid between any 2 points. So if this is equal to that, and then this is equal to that, and then this is equal to this, that means this is equal to everywhere. Right? That's exactly what we have from the energy equation. That's this point one, this is a P in, P out. In and out are arbitrary points in the field. And they're exactly the same, this sum, as long as you don't have the friction, you see H loss, and the pump. These are all the frictional field. Now everything matches in the same consistent framework that we mentioned before. Right? So now we did one example, and this is the next example. Today we're going to do more examples, and then we're going to go to the chapter 7, differential form. Differential form is also very important. But before we go to differential forms, I want you to cover more problems here. So here, in this problem, you have a pump, and this pump, you have the volume rate for discharge is 80 kiloliter per hour. And at point A, obviously gives you the pressure because it's inside the pipe. And do you see it very well? That's one thing I didn't ask.
Oh,
Yeah,
it seems to be
that's
coming
very
out.
good. Good enough. So you have the pressure A. Why? Because this is inside the pipe. It's not exposed. So it's greater than atmospheric pressure. It may be a smaller, lower than atmospheric pressure. In that case, it's vacuum. But here you've got a gauge pressure, 50 K gauge pressure. And then at point B also it gives you a pressure at point B, which is, you have a little bit of 5 times the atmospheric pressure. And then it says there is a filter here. So what's the effect of this filter? If this flow passing through that filter, what happens to the flow?
Slow down.
It's going to, you see that even before you solve it, you know from your previous experience that the filter is going to slow it down. It's going to damp it. It's going to damp the energy. It's going to increase the internal energy because of the heat and dissipation. So you got that filter here, and that causes the internal energy. You see that delta U we had in the Bernoulli in the energy equation? That is plus 50 joule per kilogram mass. So because of that filter. And then it says we also have conduction loss. What's the conduction loss? Did you have thermodynamics or heat transfer? You didn't have heat transfer before? Let me say just very, very quickly, there are 2 types of heat loss. One is called conduction, and one is convection. Convection. So these are heat transfer mechanisms. And you don't really need to pass this course to understand it. You can see from your experience. If you imagine you put your hand on a cold object, when you touch that cold object, your hand is eventually going to get colder and colder. That's called conduction. When you're touching something. But what's a convection? Convection is in this room. You see, I see that you turn on the air conditioner, and then I see the weather, the temperature will change. It comes through the moving fluid to me. So it's heat transfer due to moving fluid. It's called convection. And then conduction is very easy. The equation is K gradient of temperature. The amount of heat you transfer is proportional to gradient of temperature, which makes sense. If you don't have temperature gradient, the difference temperature, there is no heat transfer. Your finger doesn't get cold or hot. But this one, you have to solve the energy equation in the Navier source. Hopefully by the end of this class or next class, we'll reach to that. But this is more involved than that. Computation of this is more involved in conduction. Now here it says the heat conduction loss, right? And the good thing about energy equation like that is you don't really need to solve differential equation. It's just like method of lump element or bulk. You say the entire complicated shape here, you have a conduction heat transfer of this amount. So they give you the amount without needing to solve it. So here the heat conduction loss is 250 joule per second. you see these are not joule, these are the rates, so it's dW dt, dq over dt, it's not q, it's dq dt. They say determine the horsepower that is developed by the pump, right? So find the energy of this pump, like required to maintain this pressure difference. So here, again, the control volume, you see that red line around the pump, that's the control volume. It goes from all the way inlet and goes all the way outlet. So one thing about energy equation, even though we're not going to do the triple integral distributed things like that, we have just a simple equation as you saw it here. Even though we have this simple relation, but also you have a control volume. Because what? Because we drive the equation using a control volume. So you can't just memorize, well, you know what, this is just energy. Give me the start point, the end, and I'll write it. No, you have the control volume. And the control volume tells you the detail you have to include in the energy equations. So for that, first thing you do, usually in this sort of problem, it's better to find the mass flow rate, volume rate, the inlet velocity, outlet velocity. So that's what he does. Based on, he first converts a meter per hour to the cubic meter per second. You see that? You have to do that. Why? Because when you substitute this in the equations, everything should be meter, kilogram, second. And then from that, he finds the m dot. Why do we find m dot? Look at this equation, back to the main equation. This lowercase value you see here, these are head, these are in meter. These are not in energy, these are not joule per second, these are not rate. So if you go a little bit back in the previous slide, there is an m dot that we divide everything by m dot to get the height. Right? M dot and G, m dot and G. Right? So that means you have to have m dot if you want to find the joule per second, the rate. So that's what we do here. Find the m dot, and then based on Q, you got a Q. Q is what? The volume rate, V times A. Right? You substitute the value of dA, you have Q. Q everywhere same. Why? Because you have one dot. You see that? It's just one dot, inlet, outlet. There is no another exit. So Q is same, so Q incompressible flow. So you have VA, A is equal to VB, AB. So we put values here in meter square times meters per second. You get for Q, for VA you get 1.258 meter per second, and for the other one you get 11 meter per second. So look at here, it makes sense. The inlet you get 1 meter per second, the outlet 11, because why? You got a pump here. The pump will do the work for you to increase the speed, increase the head. Right? So now back to the equation. So the point about this equation is, even if I give you this equation in the final exam, like in the appendix, because you don't have to memorize. You don't have to memorize it. If I give you this equation, you should be able to go back and get this equation out of it. Why? Because all this, you see, just put, instead of H term 1, just put the actual rate times rho times Q. Then you get factor out all the m dots, and then you get back this equation. Right? And you can only do that if you totally understand how these equations are derived. Now, in this case, you don't use this equation, you see, because they don't ask you about head per meter. They ask you about joule per second. So you use this equation. Do you see that? So this is the equation you use. And then you substitute value here. You substitute value here. So this is the rate of the heat transfer, negative 250 joule per second. Do you have the work done by pump? No, that's your unknown. You can put the X here, just unknown. That's what we're trying to compute. Do you have the work done by the turbine? Well, I don't even have a turbine in this problem. Put 0 here. Right? This is just written for general arbitrary case. Now, next one, at B, you have this pressure at B, velocity, find velocity. How did you find velocity at B? Continuity equation. That's what we did in the previous slide. And the elevation, you see, what he's trying to say is it doesn't matter your reference point, where the reference point is. As long as you get the reference point, call this elevation Z, this height. They will cancel out from both sides of equation. Do you see that? There is a GZ here, another GC here, here we cancel out. And then UB, what's the UB? You see now, you have to take out the internal energy. You can't say, I put, in the previous slide, when we drive it, we add these two and said FL, this is equal to FL, fluid loss. Now, if you don't truly understand how that FL is done, you can go back and say that was actually UB minus where? Here, in the equation. You see, we put FL, the fluid loss, but that's it. U2 minus U1 minus Q. So when you expand it, you get the energy back. Why do you need to find delta U, the change in internal energy? Why do you need that term to appear? Because you have the lost U2, the filter, right? In that case, you have it, they give it to you. Why don't you use it? So that's what we put here. Multiplied by m dot. And we already have m dot, 22 kilograms per second. After you do this multiplication, you find the work done by the pump is 10 kilowatt. 10 kilowatt, you see how much is 10 kilowatt. Now, the good thing about watts is you have some feeling about it, right? So you know that if I have a good enough light bulb, it's 100 watts. It's not kilowatt, just one light bulb. Now, if I have 10 light bulb, how much energy is that? 1 kilowatt. Right? Which is kind of, you don't want to in your home, when you go home during the night, you don't want to have 10 lights on all the way during the night. A lot of bills, right? You don't want to pay more bills. Now this guy is not only 1 kilowatt, it's 10 kilowatt, that means 100 bulbs. So if you really have this in your farm, you have to spend a lot of energy on it to keep it on, right? So you can have understanding of it. Okay, and next problem here we have okay, this problem, again, you have a reservoir, you can see here, and this pump is just taking this water with a given velocity, and obviously it's not exposed to the atmosphere, so you have internal pressure at the pipe. So the pressure inlet pressure at the pipe is 80 K, and the velocity 2 meters per second, and this pump does some work on it, so that the flow is go all the way up and then discharge at people. So it gives you the discharge rate, but the discharge rate is always just the same different vocabulary for flow rate, Q. Right? When they say discharge rate, they're talking about Q, which is VA. So it gives you VA, and also gives you the diameter. That means it gives you the A, right? Pi r squared. So you also have V everywhere. So you actually, this pump is said find the power that pump must supply the water to lift it 8 meters. And the total loss is also 0.75 meter. Look at here. So if he gives you the loss in meters. So what form of the energy efficiency you use? The one that was lowercase h. The one that everything, all the heads were written in meter. Not the one that had n dot. It's very important to see what form it is. So you just go ahead, again, once again you have control volume, even though you don't go inside that, because you just see A and B. But you have a control volume from this point, and then this is the equation you have. You see that? The form I'm using, all the heads are written in meter. There is no energy, there is no joule per second. Right? But you should be able to convert this back to the m dot form, the energy form, if required. Because in the final exam, I may give one of them in the appendix, and then you should choose the other one. And the exam is closed form, close the notes, close book, close everything. Then you have to work through it, which is just one line to get the m dot form. So here we have information based on the discharge or the flow rate, Q. You compute the velocity at B, and then the pressure at A is given, pressure at B is zero. Why? Look at here. The pressure at B is zero because it's exposed to atmosphere. It's just atmospheric pressure. It's not zero, it's 100 kilopascal. But there is also another 100 kilopascal here, which they cancel out. And it's not intuitive. You see that? It's not very intuitive. But if you do it once, which we did it in fluid statics, hydrostatics, then we realize, oh, it doesn't matter that the gauge pressure, whatever it is, atmospheric pressure, P0, you cancel out whatever you have it. So you only have gauge pressure, 0 here, and then you have ZB in this equation. There's the height at B, which is 8 meter. Now you could choose this point as a reference. Then if you choose this point as your reference, your ZB is what? 0. What about ZA? Negative 8. Don't put positive 8. It's negative 8. It goes down. If you put positive 8, your result will be different. So put it here. So when you substitute value here, you substitute for pressure, for the velocity and the pressure, and then for the height at A, which is 0. So 0 goes here, the 0 is right there. And then H pump. Do I have the head of pump? That's exactly what I'm solving for. Right? So the good thing about the energy equation, you don't have to be creative. Like momentum energy equation. You remember we did momentum, we have to be very careful what control volume, what are the inlets, what are the outlets, right? But energy equation is just write it between 2 points without paying attention to inside the control volume. And it works miraculously. And it's just one equation. Momentum was 2 equations in 2D, 3 equations in 3D. Hopefully after this we come back to momentum differential. So put in H pump, we don't know it. On the right side, we get the pressure at B, which is 0 divided by gamma 0. Velocity at B, we computed 10 meters per second, divided by 2G plus ZB plus 8 meters, plus H turbine. Do I have turbine? No, 0. Right? Now, if there was another turbine here, a blade that generates electricity, you gotta put that H turbine here. Right? But we don't have turbine here. Plus the head loss. Now, if they say frictionless, right, then you put 0 here. But look, it gives you head loss. Head loss is 0.75 meter. You see that? Do you see the cursor very easily? It's right here. So you put head loss, and then you have one equation, one unknown for H1, you solve for H1, you get 5.68 meters. That's the head of the pump. That means the pump, the physical meaning, you see this is not the distance. Even though it's in meter, this is not the distance. This is a physical meaning of work. That means the work done by this pump is such that it moves a column of water 5.7 meter up. So that much of pressure, that much of head is such that it moves a column of water 5.7 meter up. That's a lot of work, right? Now, if you want to get W dot or ddt of work, what do? You multiply the H1 by m dot, which is Q times rho G, right? So you have Q, you have gamma times H dot, you get W dot of the pump. Now this is the thing that the pump is actually, this is the energy that the pump, you see, kilowatt, 1 kilowatt, 10 light bulbs, it's 10 light bulbs. That's the energy that the pump is giving to the system, giving to the fluid to go 8 meter high. The actual energy you should give to the pump is a little bit greater than that. Why? Because the pump itself is not 100% efficient. So if you get, that's the energy that the pump is giving to the flow. You have to give the pump a little bit more energy, right? For example, if it was 90%, can you tell me, Quiz Weber, if the efficiency of pump was 90%, how much energy, do it, how much energy should I do that?
Divide that by 2.
Yeah, with the, So you divide by 0.9. So it's more than 1.1 K. How much is it? Let's do that way. 1.1 divided by 0.9?
1.23.
Yeah. 1.9 divided by 1.1 divided by 0.9. So it's 1.2 K. So you have more than, like one light bulb more. One light bulb more energy. Because the pump also is 90% efficient. Next problem, you got a jet engine. And then, before we do this problem, I want to show you another thing. When we did in the energy equation, we had this P plus half rho V squared plus rho GZ. And then there was a term U over U, internal energy, plus some other heads, with capital, as 1 meter, U over U, other heads. That was constant, right? This is the energy equation, because you are heads. If these are zero, internal energy is zero, you get what? You get Bernoulli equation. But look, if you divide this by rho, in fact, this is also work to be unit consistent. What they do, sometimes we group this together. Let's do it. They group this together, and they call it, enthalpy. How many of you guys heard this word, enthalpy? Now you had thermodynamics and you say, oh my God, that's the same item.
You can
we never get rid of it. Wherever we go, it's just following us. But guys, it's nothing except the same thing you had, but just regrouping, just organization chart. Group, regroup. Just put this together and then define this as H. And now there is another headache here. We use H for head of like friction, head of turbine, head of pump. Now there is another H, enthalpy, right? So sometimes they do like things like that, make it a little bit different. And sometimes they use another, but usually H is reserved for enthalpy. So let's write this as enthalpy form. So H and enthalpy plus 1/2 rho V squared plus rho GV plus other head other is constant. With 2 points. Now, the reason that we use enthalpy is equal to because in this problem he doesn't give you pressure, he gives you enthalpy. That means pressure added with internal energy. So it's like a net effect. When you say pressure, you're talking about hydrostatic concept. You're not talking about pressure and heat, the amount of molecular dynamic momentum that they have. But enthalpy is more generalized notation for pressure. It has more physics in it. So in this case, it says the enthalpy of the inlet is 16 kilojoule per kilogram. And then, so it gives you H at A. And then at the exhaust, it gives you 450 kilojoule per kilogram. So that's the enthalpy at inlet, enthalpy at outlet. So you have, instead of giving you pressure, you have this inlet, this outlet. So you're looking for the rest of the energy equation. Always look for a template. Look for a pattern. You don't need to be creative in the energy equation. Energy equation makes your life easier. So also it gives you velocities at the outlet, 48 meters per second. And it gives you mass, rate of mass, m dot. So m dot, you know that? M dot is rho VA or rho Q. Now, the reason here it gives you m dot, why does it give you m dot? Because it's a compressible flow. This is probably the first and last problem in this class that is compressible. That means what? That means the density of air in the inlet is different from the density of air in the outlet. In fact, density is variable in many places here, all along it. So it's a compressible. So in the compressible, not only you want to see Q, which is VA, but also you want to know information about density. So that's the reason you say m dot. But look, since you have all this in the formula, substitution doesn't matter as long as you know what the m dot is. It's rho times Q. So you already know how to work with Q. Substitution is going to be very straight. So also heat loss, Q dot, it gives you heat loss, which is 1.5 kJ per second. And say, find the power output of the engine. Now look at here. Do I have a pump here? If I take this as control volume, right? And I know, I write the energy equation using these 2 points. Okay. I have information about point A, information about point B. But what other do I have? In that equation, I had an H pump. Do I have a pump here? No. Then I have H turbine. Do I have a turbine? In fact, this is, we use different vocabulary like engine or thrust generator or engine, but in fact, this is just a turbine. You apply this high enthalpy fluid to generate the work, to rotate that blade and generate the work, right? And there is a combustion. There is a combustion there. That this combustion, in fact, on top of all this combustion gives more head to that turbine. And that turbine sucks more air, so you can also generate thrust if you want to. So, when you substitute the formula, you got to know what type of nature you have. If you have pump, you have turbine, you substitute that. Now, here, that's the equation we had, Q dot, double dot out, and then these are the head. Look at here, there is no pressure. Do you see that? He regrouped pressure, he grouped it to internal energy, enthalpy. So you have enthalpy at 2 points, you have velocities, and then put here the elevation is just 0. But just with last example, you could put Z. ZA, ZB, but because they are same level, they cancel out. And then M dot, you put the M dot here, and this is the heat loss, Q dot. Then you find W dot. What's the W dot? The work generated by thing on the system, right? So that's the problem like this. When I give a problem like in this section, I don't say this is from energy section. I just give you a problem like that, and then you have to figure it out yourself. Do you need to apply momentum equation? Do you need to apply continuity equation? Continuity equation is probably 99% of the time you have to apply continuity equation. Why? Because the velocity as one of these is given. Then to find the other, yes.
Can you explain again why that would be a turbine instead of a pump?
Because when you actually add, there is a combustion here, right? There is a combustion here. You see this hot flame? This combustion here is going to generate heat, and it's going to generate molecular momentum. And all this molecular momentum will hit the blade. In fact, this blade of this turbine here. You see, if you look at it from the side, it's like this. It's like that. And if you look 3D, these blades are very tiny. Why? So inside it, there is nothing. This blade are like this size. Why? Because there is so much heat and pressure on them that if they make it a little longer, what happens? It's going to cut it. And in fact, the funny thing about this is a very extremely high-tech technology making these blades. This blade not only is tiny, so let me draw here the exact 3D. So these are each blade. You have tons of this around that disc. Not only they are tiny, but also you have here, you have holes, and then there is a flow coming here, the liquid that makes it cool. So it's a liquid cooled or liquid conditioned object. So there is a liquid, if you look at from the top, you see that? That's your airflow. The cut of this blade, we call it airflow. There are some, it's like a pipe, liquid pipe, that goes through this to make it cool. Because there are so much heat here, so much pressure, heat. And imagine how ridiculous it is to design that cooling system. Because you got deformation, it may break. The moment you put a pipe inside of it, you reduce the its strength, right? The cross-section area will decrease, you reduce the strength. So because of that combustion, you have too much force on the blade, so you start to rotate that turbine, and then when it rotates, it stops all the airing, right? Again, you have to use continuous momentum. And then that generates a thrust for you. So that's the way the turbine works.
So instead of us putting energy in,
Yes.
it's got it already inside.
There is another way. If you don't have combustion here, right? The entire combustion is because nobody actually pushed the air in. The combustion will generate the rotation, and rotation will create the pushing air. Now, another way is to say, well, look, I don't have a combustion here, right? But I have a very huge, high enthalpy, high pressure air coming in. Then what happens? It's going to rotate that. Again, it's going to be turbine because the high pressure air will rotate. But now, if you attach something to that blade so that you actually generate energy, like electricity, like a pump in a pipe, in a pipe. So it creates a suction, then you can call it pump. So depending on what type of mechanism you actually want to use, and also in what regime. If it's subsonic, it's just a appliance home use, using it like building, they call it pump, right? And in aerospace, they may call it something else, right? So they have different vocabulary for the same concept. They have different vocabulary.
What do they call it?
In aerospace, they have things like APU, auxiliary power unit. So it's sometimes turbine, sometimes it generally acts like a pump. And so, like for example, inside the aircraft, sometimes you need to have suction to refresh the air, right? So all this energy is going to be converted in different forms. So they're just the same physical concept, but different vocabulary. Now, this problem is, let's finish this, and then hopefully we have a little bit of time to go over the differential. So, yeah, let's finish this problem and then we go to differential. It says water, you have a static here, you see this height, it goes down, but just tiny a little bit, the speed is almost 0 at 8. And then you have 150 meter long pipe. So from here, you see, all the way to here, all the way to here, this length is 150 meters. But look, this height is 40. So that means this drawing is not drawn in the scale. Because 100 is this 40, 150 is going to be all the way to the right. You see that? So it gives you the diameter of the pipe, and this goes through the turbine, so it rotates this head here, the energy will go, the pipe gets more velocity, so it generates rotation on the blade in the turbine at point B. And then it exits at point C, and it also gives you pipe diameter, and also heat loss. Every 100 meter, you have 1.5 meter head loss due to friction. So how many meters do I have? 150. So 150 was divided by 100 times 1.5 is your total head loss for this entire length of pipe. So that's what you know here. And then the velocity at the outlet is given, and say, find the power of the turbine, the power that is generated by the turbine. But look, they say the efficiency of turbine is 60%. In the last problem, I said the efficiency of pump, let's say it's 90%, but I say 60%. So what does it mean, efficiency is 60%? That means whatever I get out of the energy equation, I have to multiply by 0.6. Right? It's not gonna give me that much thing that I get from energy equation. Some of those will be damped inside the turbine, and I only get 60% of it. Let me just write what it tells you. It just say, write the energy equation between A and C, here, all the way goes here to C, and then compute the head of the turbine, and then finally, before recording your number, multiply by 0.6, because the energy of that is 60%. So that's what we do here. So you have velocity at A is 0. You see approximate to 0 is not 0, but you take it as 0. Pressure at all points are 0. You see at A you are exposed to the atmosphere, at C you are exposed to the atmosphere. And then the elevation at A is 40, ZA is 40. The elevation at C is 0. But again, you don't need to freak out. Well, should I take this as my reference? Or whatever you take, if you stay consistent with your notation, it should work. The end result must be exactly the same. So you put in this equation, you see this is the head form, so everything is metered, do you see that? Now when you get the value here, when you get H of turbine, right? You should not report that number. Why? Because this number you get here is in what? Meters. What the question asking you is get it in what? Again, you have to compute your flow rate and gamma and multiply by flow rate gamma to get the rates, the watts. Do you see that? And it's very easy. It's not really hard to forget to do that. So here, go ahead and substitute value PA 0 over gamma VA 0. Z at A is 40. H of pump, there is no pump here, 0. And then P at C is equal to right here, again 0, exposed. B at C, which should be either given to you or we can compute it from continuity equation. And Z at C is 0. And then H turbine, yes, I do have turbine. And what about H loss? Head loss? You remember I just talked about it a few minutes ago? You said head loss per 100 meter is what? Then we have 150 meter. What do you do? 150 divided by 100 times the head loss. You see that's exactly what it does here, 1.5. So that 1.5 was head loss per 100 meter. If you have 150 meters, you do this simple proportion. You put it there, you get a head of turbine is this. But look, you need to multiply by flow rate times gamma, or mass flow rate times G. That's the way we drive the equation, right? So you multiply that, and you get the total head work is the total work done on the turbine is 5.3 kilowatt. Again, it's not huge. You see, it's not huge. But look, is this? Are we gonna get the same thing? Like if I connect the battery to that turbine, am I gonna save this much energy? No, because the efficiency is not 100. So you multiply that by 60% to get 3.19. That's what you actually can store in the battery. That's the energy that goes to the battery. Now, if you have the in the final exam, not final exam, maybe next midterm, we put. I say we have a battery that can store 1 kilowatt per hour. How long would it take to just make the battery full, to charge it up, if you connect it to this turbine? Then that's one of the questions. So how do we solve it? Well, you have this per second. You see, this is D work, D energy per second. So that means because the rate is same, if you multiply by time, you can see how much energy is going to be sent to the battery per unit second. Then you can make proportional with the amount of battery energy saved per unit second, and you can say how many seconds it takes to make the battery fully charged. So it's very, very, very simple. So the main core is this. This is energy. Now, before actually we leave, I want to say this. Next class we go to differential form, chapter 7. But I want to summarize what we have. And next class we are going to discuss this in detail. So what we have is this. Rho dV plus surface integral rho v dot m ds 0. This is, I don't write the name of it to you right now. Rho v dv plus surface integral rho v dot m ds is equal to negative p n dot ds plus f external and then rho t equal energy, then you get rho e dv plus surface integral rho e v dot n ds is equal to q external plus w v dt v dt w external. So look at these equations. How many equations are there?
3.
Who said 3? Are these 3 equations?
Well, they're all kind of the same.
No. They are very, very, very different. How many equations are there? In three-dimensional space, how many equations are there?
9.
What is this? It's a vector. So you have UVW, 3 components. So how many equations is that?
3.
3. How many equations is this?
1.
This is always 1. Right? It's a scalar. How many equations is this?
1.
1, a scalar.
So there's 5 equations?
5 equations. So 3 here, 4, 5. What is this equation? Continuity. What is this equation? What is this equation? Conservation of energy, conservation of momentum, conservation of mass. This set of equations are 5 equations in 3D. What about 2D? How many equations in 2D?
4.
2 here, 3, 4. So this system of equation, they call this the Navier-Stokes equation. Later, if you put contribution due to viscosity or shear stress, then this equation I call it Navier-Stokes equation. In fact, they used to call the momentum with the shear stress Navier-Stokes, but they usually call this the Navier-Stokes equation. Now, if you can solve this equation, you can solve pretty much every single problem in the field of mechanical / civil engineering. But you cannot solve problem in chemical engineering because the component, the fluid will react. You have reaction. Then there are additional equation. They call it species transfer. Or species transfer. But we're not equations. We're not going to solve those transfer of components like multi-component reactive flow. We're not going to do that. All we need is these 5 equations. If you can solve these 5 equations, you can solve every single problem in the field of mechanical engineering, including dynamics, the fluids, thermodynamics. On top of that, add to this the equation of the strain P is equal to rho RT, equation of state. So these are together, they call all of these the Navier-Stokes equation. Well, if you can solve this, you can solve every single problem. Now, next class, I'm going to convert these are the integral form. I'm going to convert it to differential form, the derivative form. And then we use that to solve actual practical problems.